She's going to be speaking about real-time communication at scale, which I think is for Facebook. So, Li-Tal, take it away.
Hello, everyone. My name is Li-Tal. I'm coming from Facebook. In the last 2 years, I've been managing a team in Messenger RTC. So the team that I'm supporting is responsible to media quality on audio, video calls via Messenger, and also some additional products that I will show you in a few minutes. So in this talk, I will talk about the scaling challenges that we have in Messenger. So when we are talking about scaling challenges, there are several different dimensions. So obviously, first of all, there is the dimension of number of calls. So calls over Messenger is a growing product. We see more and more users using Messenger in order to do calls. And we also see shift from audio calls to video calls. So more and more people are doing now video calls than audio calls. So yeah, this year we have more video calls than audio calls. So this is the first challenge, to build a system that can scale to Messenger scale. As much as I know, Messenger is the biggest WebRTC product with the highest number of users. So beside the dimension of the number of calls, we have also the dimension of the dimension of calls conditions. We have users all around the world with different network conditions, with different network standards. We have users with many different diverse types of devices. Android has a long tail of thousands of devices with different capabilities. So just to build something that will work on all those scenarios, even before we are starting to talk about the quality of the media, is a big challenge. So in this environment of growing number of calls and growing calls conditions, we are trying to push and improve the video and media quality. So this is the challenge. Many times something in lab will work very well, but once we will start to test it with real public users, we will see tons of issues and regressions in quality. So in this talk, I will cover these 3 different dimensions. Our approach to scale the number of calls, to support the different calls conditions, and then I will give an example of a project where we were trying to increase media quality, and I will basically show you the challenges to do that at this environment of scale. So first, let me start by introducing the products that we are supporting. So Messenger, in case you don't know, is this app where you can instantly connect with your friends. Beside the chat, we also support audio calls and video calls. We have iOS client, Android client, and we are also supporting most of the browsers. So beside the 2-people calls, we also support group calls. So as you are in a chat with a friend, you can keep adding more participants to the call and make it a group call. We support this grid view and also this dominant speaker view. And we are also supporting these fun features of adding masks and filters on top of the video. This is extremely fun when you are chatting with your kids. Beside of that, there is another product that we are testing that lets you play games while you are in a video chat with a friend. So with this product, there is some additional pressure on the network and on the device itself, so it comes with some more complications. So beside Messenger, we are also supporting video chat in Instagram. So this product was launched globally yesterday. Instagram, in case you don't know, is also a super popular app owned by Facebook. Instagram hit recently 1 billion with a B users every month. I think there are only around 5 apps with more than 1 billion users. So basically, once Instagram started to work on video chat, we made a decision to reuse all the backend infrastructure that we built for Messenger, also for Instagram to save some engineering work. So we have the same infrastructure supporting Messenger and Instagram. So beside video chat, we also support the live scenario. So both for Facebook and for Instagram, we have this feature where people can broadcast in real time to the public, and they can also invite a friend for their broadcast and basically broadcast to the public in real time the video chat with a friend. So we have this product in both in Instagram and Facebook. So those are the big products that we are supporting. Messenger is still by far the biggest product. So here's some data about the scale of Messenger. So video, as I said, is a really growing product in Messenger. In 2017, we had twice video calls than we had in 2016. We had 17 billion video chats. Messenger has more than 1.3 billion users, monthly users, and 400 million out of them are using the product to do video and audio calls. So even inside Messenger, we still have lots of room to grow. And Messenger is the second most popular iOS app of all times. Do you know which is the most popular app? Facebook, right? Okay, so this is the scale and overview on the products. So now let's talk about scaling number of video calls. So I will start by giving an overview of our architecture. So our architecture is based on WebRTC, 1122, based on WebRTC. In Facebook, we started to contribute to the open source in the last year. So we really want to get more involved in the open source community. So there are two types of connections: signaling in order to set up the call and negotiate the conditions of the call, and then the media connection in order to send the media streams, audio, video, and data streams. So let's start with signaling. So in Messenger infrastructure, we are using services called MQTT, which is also a public protocol. And those services are basically serve as a proxy to the end users. So they have persistent connections with the end users, and they are sitting very closely to the end users. And then when Alice wants to connect with Bob, we need to discover what are the active devices of Bob. Like in Facebook, you can be active on your desktop and several mobile devices at the same time. So for that, we are using the routing service. Routing service will find the active devices and route the signaling messages to the right MQTT service. In many cases, that will not be enough. As you know, users are sitting behind the NATs. And then in order for users to discover their public IP address, in Facebook, we are hosting our own STAN servers. So STAN servers is a very basic service. It gets requests and responds with the public IP address this request came from. In more or less half of the calls, that still will not be enough, and this is because users will sit behind firewalls that will block requests from unknown sources. And for that, we are hosting also our own TON servers in Facebook. So basically, TON servers, they will have public IP address. Users behind firewalls will be able to establish a connection with the TON servers, and then in most of the cases, media streams coming from TON servers will be acceptable by the firewalls. So this is the architecture for two people calls. We are also supporting the scenario of big groups, and for that we are introducing another service, the Multiway service. The Multiway service is basically a routing service and also media service. So each user can have media connection with the Multiway service, and the Multiway service will take care of sending the media streams to all other participants. So why do we need this multi-way service? So this slide is very similar from, probably you remember it from yesterday, from Lindsay's talk. So another approach that we could have taken is to go with the mesh topology, where each user has a connection with all other participants in the call, and as we are adding a new participant to the call, we will add a new link from all existing participants to the new one. And there are advantages and disadvantages for this approach. On the good side, this is super simple. So we need very little backend infrastructure in order to support these types of calls. So with this approach, it's actually very easy to scale number of calls, because beside the tone servers, we don't need to add too much backend infrastructure. On the other hand, it will be much harder to scale the number of participants in a group. And also it requires a lot of uplink, since each participant needs an uplink to each one of the other participants in the call. So the second approach is to go with this star topology, where each participant in a group call has uplink to the multi-way service, and the multi-way service is sending those streams to all other participants. So for that case, now group size will not impact the uplink. It will be much easier to scale the size of the group. And also now when we have this multi-way service, we have the opportunity to do mixing and to do some additional work in our backend. On the negative side, now it is much harder to scale number of calls, because now we are limited by the capabilities of the multi-way service. And also, once we are adding this additional service in the backend, we are increasing the latency from one user to the other user. So in Messenger, similar to Slack, we made a decision to enjoy both worlds. We noticed that most of the calls will be super small groups. Most of our calls will be 2-people calls. And in that case, we don't need multi-way service, and we can have direct connection between the users. And then once the group is getting bigger and bigger, in this example, Alice is inviting Chris to join the conversation. At this point, we will connect to the multi-way service. I think this is different than what I saw from Slack. We don't have two connections, this connection in the background. We will do that only once we will see that the group is about to grow. So we will establish this new connection with the multi-way service, and basically we will swap from a direct call to multi-way service call. And once we have that, we can ring to the additional user to join the call. So when we built that, we had several concerns. So first of all, we had the concern of latency of this process, since we need to establish a new connection and swap, and we had concerns that it will not be a good experience for our users. So we invested a lot in make it very smooth for the user, the feeling of adding more participants to the call. And then we had a concern of regression in quality, as we are adding more participants to the call. So we invested a lot of work to close the gap of quality between direct connection and connection through the multi-way service. So that was the part about scaling the number of calls. So basically, for most of our calls that are 2-people calls or very, very small groups, we are not adding too much additional infrastructure to support that. So for the second part, I will talk about scaling to different call conditions. So in general, the goal of my team is to have the best media quality to everyone. But many times we will work on building new features, and in the lab everything will look great and awesome, and quality will be really good, and we will enable those features to Facebook employees, and we will get great feedback, and everyone will be happy. But then once we will enable that to the public, we will start to see problems and quality regressions. And this is because of this huge diversity in cause conditions that we have with our users. So first of all, the diversity in devices. So there is a variety of qualities, long tail of Android devices, thousands of devices with different capabilities. And different capabilities is different camera capabilities, CPU, codec supports, battery capabilities. So it makes it a real challenge to build something that will just work on all those devices. Another challenge is the network and the variety of networks that we need to support. So this image is, I don't know if you're familiar with that. So basically it shows connections between two people in Facebook. So you can see lots of connections like here in the US and in Europe, and you can see the international connection between the continent. So we need to support many different networks, Wi-Fi, cell, different standard, 2G, 3G, 4G, and again, it is really hard, like networks with different behavior, and it is really hard to build something that will just work. So now let me go through the architecture on the client itself, and I will try to highlight these two challenges and how are we trying to mitigate that, the device, the diversity in devices and network conditions. So let's start with capture. So we are starting with the camera, which is device specific. And then we have the logic to do face tracking that we need in order to do all those nice masks and filters on top of the video. So here, if the device support that, we will use hardware accelerators in order to save CPU and save battery consumption. Then we have a step of doing some pre-processing before video encoding. And then for video encoding, again, it depends on the device. Some devices will have hardware support. In some devices, we will do encoding in software. And it is really challenging, since some devices will say that they have hardware support, but in reality, the implementation will be very poor. In many cases, the encoder implementation will be optimized to the scenario of capturing video in a high bitrate and saving it locally on the device. But once we will try to encode video in low bitrate, we will see a lot of problems in quality. So here we need to make the decision whether to do it in hardware or in software. In some cases, for example, for simulcast, we will have more than one instance of encoder. And then we will do the RTP packets, and we will send the data through the network. We also have this feedback loop to help us estimate the capabilities of the network. And this is actually a crucial component for video quality. And I will talk about bandwidth estimation in a bit, in more length. So since we have so many different network conditions, and network can change and have interrupts during the call, bandwidth estimation logic is really critical for the quality of the video, and it provides feedback for the encoder, and the encoder can change the bitrate according to the conditions of the network. So the challenge with bandwidth estimation is latency. We would like to estimate the capabilities of the network before we are starting to see packet loss. Once we see packet loss, the video quality is already pretty bad. So the way we are doing that is by measuring the latency, delays for packets. And the idea is that as the network is getting more and more congested, we will see the buffers in the different routers filling up, and we will start to see delays. So going back to this diagram, Alice is sending video packets to the Multiway service. Multiway service is sending those video packets to Bob and Chris. Multiway service will get feedback from Bob and Chris, transport feedback, which is basically those delays between packets. And the Multiway service will use this information and the packet loss information in order to cap the max bitrate to ask from Alice. So Multiway service will communicate that back to the sender using REMB, and also will send back transport feedback, which is the delays on this uplink between Alice and the Multiway service. And then the sender side, we will feed this information to the encoder. And if we detect that the network is congested, we will reduce bitrate. And once we will see that the network is recovering, the encoder will keep increasing the bitrate. So to complete the picture, this is the architecture of the side. We are getting from the network the packets. We are sending back the transport feedback. We have the jitter buffer to reorder the packets. And we are doing video decode, which, again, here we will make the decision whether to do it in hardware or in software. Many devices that is failing to do encoder properly will be able to at least do decoding in hardware. And then we will render the video. Okay, so for the third part of the talk, I will talk about improving media quality at scale using a case study. So this slide also should be familiar. Varun also used a similar one yesterday. So when we are thinking about improving video quality, we need to take into account this trade-off between video quality, battery, and data. Different users will value each one of those elements in a different way. Some users with weak devices will care the most about battery consumption. It will be really bad experience if after 5 minutes of call, their phone will die and they will not be able to do anything else. Some users will have a limited data plan, and the thing that they will care the most is just about saving data. And some users that are sitting at home connected to Wi-Fi, they don't have any problem to charge the phone, they will care the most about video quality. So as we are thinking about improving quality, we need to think about all our users and this trade-off between those three elements. So the case study that I will talk about is increasing max bitrate. So in this project, basically the idea was that if we will increase the bitrate of the video, we will get a video with higher quality, and our users will be happier, and we will see that in our star ratings. So we will see higher star ratings, more 5-star ratings. And we increased max bitrate, we gave it to Facebook employees, we got great feedback, everyone were happy. And then we started to experiment that with the public. So the way we are doing it in Facebook, we have lots of users. After we are getting initial feedback from Facebook employees and we see that things look good, we enable to like small percentage of our users and starting to do A/B testing. So we started this initial experiment with the public. And then we saw that increasing bitrate actually reduces the top metric. More specifically, we saw that we are getting more one-star ratings from our users. And then we started to investigate what is going on, and we had several lessons that I will share with you. So first of all, we noticed that as we are increasing video encoded bitrate, we also see battery consumption going up. So this graph is showing you battery consumption per minute as a function of video encoded bitrate. So then we try to understand if there is anything that we can do in order to mitigate this increase in battery consumption. So in order to explain you what we did, I will talk for a minute about the difference between bitrate and resolution. So bitrate is the amount of data used to encode a video, and resolution is the amount of pixels that we need for each frame. So we can increase bitrate and use that in order to increase the resolution of the video, or we can increase the bitrate and use that in order to get higher quality from the encoder. And then let's say that we are capping the bitrate to 2 megabits per second. We can, if we will cap the bitrate and we will just try to increase the resolution, so now the encoder needs to do more work in order to hit this bitrate cap. So more work means more CPU. So this is what we saw in our experiment. So we did one experiment group where we increase the resolution, and one experiment group where we just increase the bitrate in order to get higher quality from the encoder. But if we will use the same bitrate with lower resolution, we will not see any impact, almost any impact on battery consumption, and we will see improvement in quality. So basically, the conclusion here was to increase the bitrate in order to get higher quality from the encoder with lower resolution. Yeah, so that gave us back some star ratings, but still not enough. Still not enough in order to be able to launch it globally. So then the second thing that we noticed with the experiment is that as we are increasing the max bitrate, now the users experience a drastic star topology. Then I talked about the different pulse conditions and how can we support the diversity of devices and the need to really invest in bandwidth estimation algorithms in order to support different network conditions. And then I talked about improving video quality and showed you this trade-off between video quality, data consumption, and battery consumption in practice in a real project that we've been working on. So thank you very much. I will be happy to answer questions, but this is also my birthday. So one second, you can do it again. Yeah, now. Thank you. One second, another selfie. It always go to Facebook, you know. Thank you.
Happy birthday.
Thank you. Yeah, now I can take questions. Yes.
How much different are the challenges, the headaches between endpoints, Android, iOS, and in all these negotiations?
Yeah, Android is
difference?
Android is a huge headache, definitely. So iOS is much more reliable. In many cases, when we will work on a new feature to improve quality, we will start with iOS, and Android will take much longer time.
And is this because of FaceTime and all the developments that came before on iOS, or not?
I think it is just more reliable, and with Android there is this challenge of a long tail of devices with different qualities. So
Right.
yeah, for Messenger you will see that our average user will have devices from 2012 year class, so relatively old. Yeah, iOS is more reliable from my
Interesting.
experience.
Thank you.
Hi there, just two questions. So at Facebook, all the WebRTC stuff, that's all native. So that's iOS and Android, native platform, no React Native in that platform.
So so we have, I don't know if it is relatively to other teams here, but we think that we are a relatively small team, so we will try to reuse as much as we can across platforms. So as much as we can from our stack, we will try to have in C++, so we will be able to have, you know, one code base to support and use on different clouds.
So you're using the NDK really for low-level kind of integration?
So we are using C++,
Okay.
and then APIs for iOS and for Android.
Okay, and then my second question is just regards to the turn servers and the stun. What's the percentage of people you're seeing on the stun versus the turn servers?
Yeah, so I think it is 1 to 8. So stun server are more, you know, they have stun servers that are doing basically nothing. Stun server, they need bandwidth, so you need more of them.
Okay, so is there still a lot of people going through the turn servers? in terms
So
of-
yeah, more or less half of the calls will go through Tone.
Okay, thank you.
I have a few questions.
Sure.
On your pipeline drawing, you didn't put any encryption. That's because you simplify it, or that's because in some cases you do not encrypt?
Yeah, good question. We are doing encryption. So we are encrypting the calls. I think it is again similar to the Slack diagram.
Mhm.
We
And also-
don't have end-to-end encryption. We have encryption, decryption on each hop.
Hop by hop,
Yeah,
okay.
yeah, yeah.
So between the UDP packet and the RTP packet,
Yeah.
you terminate the DTLS, right?
Mhm.
So there is a lot of things you do that you can only do on native, like
Mhm.
the bandwidth estimation, modification, and things like that. But you do have a web client. What do you do when you negotiate between the web client and the mobile client, for example?
Yeah, this is a good question. So web client is a headache for us. Most of our users are mobile users, and we consider ourselves mobile first company. So many of the things that we are doing, web is a bit behind. Yeah. So
Okay.
some features will be missing.
All right, I had the third question and I forgot, so.
We can go back.
But if you use REMB, probably it doesn't make any difference to the web client?
Yeah. We are using REMB.
Any other questions? All right. Well, thank you. So, Tim, you want to? You remember? All right. Remember, and then Tim.
Sorry, very quick one. You use the webrtc.org code, or you have your own stack for the mobile?
So what happened is, I think when we built the audio calls 5 years ago, WebRTC was still not focused on mobile, and we were building mobile first right from the beginning. So back then, it made sense for us to branch out of WebRTC, the open source. But over time, we are doing lots of effort to merge back. So our goal is to merge back and contribute all the improvements that we have to the community.
All right. Well, thank you so much. Really appreciate it.
Thank you.
Have a great day. So I think that's a break for lunch then now, right, Dan? And I'd like to point out also that there's an advisory notice for this afternoon that the